Hey, good morning, everybody, and welcome to our first in a series of webinars on EAW adaptive technology. I'm Robert Scovill. I'm the Senior Live Sound Market Manager for EAW, and I'm going to be joined today by my good buddy Jonas Domkus. Hello, Jonas. Welcome in, buddy.
Hey.
Jonas is the Technical Sales Manager for EAW. We are going to break this webinar today into kind of two sections. I'm going to take the first half. Jonas is going to take the second half. I'm going to kind of get under the hood with adaptive a little bit and kind of tell you how it works and why it affects sound quality and it sounds so good. And then Jonas is going to take you into the real world and give you a couple of case studies and do some actuary analysis of what it costs and how it can be really competitive in the world as we know it. Okay, so we also hope to do a little bit of myth busting out there. You know, adaptive's been around for a little while, and there's a lot of, dare I say, misinformation out there about it. So we want to try to help clean that up a little bit. And we'll do that certainly over the series of webinars here. This is not going to be the last one of these. We're going to have a series of webinars, kind of, there will be blog posts that are associated with these webinars that do a little deeper dive, et cetera. So I encourage you to stay in touch with the EAW website. This is all being built as we speak, and we'll get this up and running and hopefully get some solid information in your hands, and you guys can go out and make your decisions based on that. All right, so we are going to talk about the adaptive advantage today, and I don't think, in terms of talking about like kind of an origin story for adaptive, you can really talk about this effectively until you can kind of ask and answer this question, right? Why line array? Why did we go to line array in the concert sound industry? And, you know, really when you ask this question and you answer it, you start to realize really the underlying thread of all of concert sound design was trying to get to this idea of a point source, right? Where we have audio for a big audience that is acting like a point source. You know, in the earliest days of it, we put together multiple point source boxes into big arrays. And of course that had its challenges as well. And we always knew line array was kind of sitting in the background there. The math and the concept has been around for a long time. And you have to ask the question, why didn't we get there earlier? What was preventing us from getting to line source for concert sound? And it came down to a couple of really simple things overall. We didn't have the driver technology to be small, right? We needed small, very powerful driver technology to be able to reach the line source criteria that was established decades ago. You know, this math is not new. It's been around for a long time. But we just simply didn't have the componentry to be able to do full range line source at concert sound levels. We didn't, because it requires small componentry to be able to do that. So how did we get there in the mid 90s? Well, you know, we could get to line source and meet the criteria up to a certain frequency, and then things got challenging. And as you're going to see today, I'm going to try to walk you through this a little bit today. You know, we decided to, I don't want to label it as bailing out, but we decided to go to a horn and an isophasic waveguide to offset the problems that we have with small drivers, right? Or the challenge we have with getting to a small driver is what I should say there. But the cool thing about this, and really I'm kind of on a little bit of a crusade about this, is that EAW did not do that, right? The engineers at EAW said, okay, if we're going to go line source, let's go all the way, right? We want to be able to have the small drivers in place to be able to reach the highest frequencies because this is music production, right? We need to have it available for music production. This is not just speech we're talking about here. So they decided to go all the way down the path here and create something that was indeed a single acoustic source. It was going to act like a point source and have it be the full frequency range, right? So I love that idea of just not conceding to the moment and actually making it happen. All right. So what was the big advantage in going to line source for the concert industry? I've said this for many years, and I said it in the earliest days of line source. What it did was give us a method, right? It gave us a way to actually intentionally attack coverage of a seating geometry, where as opposed to kind of flying by the seat of our pants, line source and the associated predictions were going to be able to allow us to do this very effectively. So it gave us a really consistent approach to doing this. So, you know, we kind of went to this mindset of how do we predict coverage? when in fact, what we really should be talking about is not predicting coverage, but how do we use the line source to adapt the coverage to the seating geometry, right? We're not just concerned with where the coverage starts and where the coverage ends. We're actually concerned with everything in between those two things and making sure we're addressing a geometry appropriately there, because it's not just linear throughout that range of vertical coverage. It's different, right? So how to adapt coverage is what we want to do. And to adapt, it means you have to start as a single acoustic source, right? If you're going to do that, you have to have the entire frequency range covered in single acoustic source. The second part of it, of course, is you have to define a polar response. You have to take your array and say, this is what I want the polar response to be in order to facilitate this coverage, right? Now, there are a couple of ways that you have to do this in order to adapt. First is create a single acoustic source, as I mentioned, right? How do we create a single acoustic source? The source size must be small, right? It must be small relative to the passband that it is going to present to the audience. The second piece of it is the distance between that source has to equal the size of the source, the spacing, the center spacing between the units. Meaning if we have a 2-inch driver, then it has to be 2-inch spacing between the acoustic centers. 1 inch, it has to be 1 inch. 1/2 inch, it has to be 1/2 inch in order to meet the line source criteria, right? So you can see already the challenge of that. You know, in the mid 90s, when we were just switching over to line source, the idea of having 1-inch drivers spaced this way to be capable of producing sound reinforcement levels would have been a big challenge, right? So that is the thing. But you have to be able to meet this criteria if you are going to state unequivocally that you are a single acoustic source, meaning your entire array is acting like a point source, okay? So let's kind of go down this a little bit. Let's just look at a 1-inch driver. This is just a raw 1-inch driver. And as kind of predicted, you can kind of see I've got just a range from 1,000 hertz out to 12,500 hertz shown here. And it is omnidirectional, as you would expect, you know, for the most part. If we take a look at a 2-inch driver, oh, I should state too, this is vertical polars as well, right? Remember, guys, we're looking at this up and down, right? We're not looking down on the array or down on the device. We're looking right at it. So this is a vertical polar that we're talking about here. So if we go to 2-inch now, you can still see this, that we have similar result. We have, you know, it being primarily omni in direction all the way out to 12,500. But as we start to stack these drivers, as we know, you know, as we start to stack them vertically, we're going to create collapse, but we're also going to create other issues. And that's because of the timing offset, right? As we move off axis of it, there's going to be different arrival time from the top one to the bottom one, and it's going to create some issues for us. And, you know, Olson kind of sorted this out in the line source criteria, saying, okay, if you're going to have this kind of spacing, you have to match this criteria to be able to have control out to a given frequency. And of course, this frequency is dependent upon the spacing. So at a 1-inch spacing, we can have full control of this line source that we're creating out to 13,500 hertz. As we move that to 2-inch drivers and stack them, that stops at 6,700 hertz. You don't have the control above that because of the offset spacing between the two drivers. Okay, I'm going to kind of show you this here. So here's a pair of 1-inch drivers stacked together, and as we can see, it starts to collapse. We start to see that collapse. We get, you see the narrowing of those frequencies in the high frequency and the lower end of this, as predictable, right? And as we add more and more drivers, the collapse becomes more and more extreme. So let's take a look at 2-inch drivers now. 2-inch drivers, similar thing. We start to get some collapse. We start to see the frequency bands scatter a little bit to the top there. But the same sort of thing is happening there, right? We get the collapse, which is what we want. Now, as we move up in driver count, this is where it gets really, really interesting. And I'm going to focus on the high frequency here because that's where the rubber kind of meets the road here. So here we have 8 1-inch sources stacked together. And you'll notice that what happens is we get this really beautiful collapse all the way out to 12,500 hertz. We get no side lobing to speak of. Everything is kind of pinpointed to the front of the array, right? Which is what we want. And why do we have this? This is an important, fundamentally important piece of information to have. We are able to create this because there is so much overlap in these drivers, right? Remember, they started as omni. Now we've stacked them together and created this very narrow pattern. It is honestly is really analogous to what we do with subwoofers, right? Why can we steer subwoofer energy so dramatically? Because there's so much overlap in it, right? So the overlap is a key tenet of this whole thing, this whole process. So we see that there, right? So let's take a look at this with 2-inch drivers. And of course you think, okay, well, that looks really good. That seems to be collapsing very well until you realize that this is only up to 5,000 hertz, right? Once we get above that, then we're going to start to see issues again. And again, it's that spacing issue. So when we get out to, take it out to 12,500, now you start to see the side lobes start to happen. And the acoustic result of this is that high frequency feels more diffuse here. It doesn't feel impulsive. It doesn't feel like it's coming from one thing. And it's really noticeable on, as a mixer, it's noticeable on things that have high frequency transient in it, percussion, cymbals, S's on vocals. They all sound wide here. They don't sound precise. They don't sound clean. Like you would hear on a control room monitor where you only have one source of high frequency, you would be able to monitor that frequency range really effectively here. That gets very, very tough to do here. This does not sound right in the field as we stack these together, right? So this was the challenge with line source in its early days. Well, what do we do? How do we attack this and clean this all up? And of course, the idea was to come up with put the high frequency element on a horn and use an isophasic waveguide and regain control of that high frequency, right? So that's kind of what we did. You guys are all aware of what's happening in isophasic these days, I'm sure. So here's a 2-inch driver on an isophasic waveguide, and voila, look what happens here. We get a very controlled and very narrow output, right? Now, keep in mind that, we put these on these isophasic horns and we've, declined the overlap here. We've taken away any ability to overlap for the most part. I mean, these are 10-degree horns, 10, 12-degree horns, something like that. But we have achieved the initial goal was to get all the frequency, at full bandwidth to exit this thing in phase, isophasic, right? Which we achieve with that unit. But as we start to stack it and we start add more components, that's where the trouble kind of starts to head back our way. If we stack 2 of these units, we still get a pretty good collapse. We really do. It's still pretty good, but we start to see some splintering of that high frequency again, and it has to do with this spacing issue. We start to see some scattering of high frequency here again, and it kind of reducing in level off axis, right? So as we stack up a whole bunch of these, as we stack up a whole bunch of isophasic horns, we can create this collapse, but as you can see there, even if we stack up 8, that scatter starts to get more pronounced, and it doesn't act like a single acoustic source here. This is not acting like a single acoustic source. Whereas with adaptive, this is an example of an Anya enclosure with 14 high frequency devices there. You can see that it is beautifully collapsed, right? We have all of this information beautifully collapsed here. Now here's the secret sauce, right? Remember, in this situation, we've stolen the ability to overlap, right? This is all just being measured out at distance of the full array. So we see the full collapse of it. Here we're doing the same thing, but given that we have the overlap and we have DSP available for every driver within this horn segment or array segment as it would be, we can actually create any size polar, any shaped polar is what I should say there. Anything between that and that. We're essentially just releasing audio back to where it originally wanted to go, right? And by doing that, through use of delay, equalization, amplitude, all very, very basic DSP components, we can create a polar of nearly any shape in that vertical setting. If we go here, we can't really do that, right? Even if we put DSP on every component here, our ability to reshape the polar is not really there. We don't have the overlap between the horns in order to be able to do it to any effective scale, right? So, and we'll kind of dive in on that going forward here. So, I'm fully willing to concede that, the isophasic waveguide is a good thing. It works. It does what it is intended to do. But here, by comparison, you're looking at one isophasic waveguide on a single driver. Well, this would be considered one high frequency element in an ANYA enclosure. This is 14 high frequency devices, and it in and of itself is isophasic. It is single acoustic source, right? And this really starts to show itself as we start to add more components, as we start to stack, right? So you can see really as we stack the isophasic pieces here, what we are actually running into is we're turning the high frequency element of the array really into more point source like array, right? It's certainly line source up and to the horn, but once we get to the horn, it is actually just point sourcing a lot of these this high frequency information into the listening space. Whereas we're looking at 8 enclosures on the left, well, we're looking at 4 adaptive enclosures on the right with a total of 56 high frequency drivers, but yet it's still acting like a single acoustic source. It still has all of that capability to expand or decrease the polar vertically. If we're going to expand or decrease the polar in the isophasic example, we have to angle it, and we need more cabinets to cover a wider vertical angle, right? So as soon as we start angling it together, then the breakup of this high frequency information becomes even more pronounced above the critical spacing thing. So I tried to bring some receipts with me here today. I guess that's how we would put it. And we're going to look at some of this in F chart to kind of prove this. So this is an example of a person standing directly below a mechanically articulated array that's hung flat. And we're going to, analyze whether this is actually a single acoustic source or whether it's, some sort of hybrid here, right? So if we take a look at this, well, the low frequency and the low mids is certainly acting like single acoustic source. All of those components have met the line source criteria, and it's turning out great. That is acting like a single source up there. But in the high frequency, it is certainly not doing that. This is not a single acoustic source, and that's kind of evidenced by, you can see all of the impulses here showing up in the F chart. Now, I know I have some cohorts out there that work in concert sound, and we've been around this for a long time, and we've all done this walk vertically with line source. And I couldn't count the amount of times somebody has said to me, ooh, I've walked out of the horn. I walked in and out of the horn there. Did you hear it? Yes, this is what you're hearing there, right? Because that high frequency element is not a point source. It is a point and shoot in order to create the coverage pattern in mechanically articulated, right? So, I had people, I put this in here specifically for this because I've had people respond and say, well, you just don't have enough cabinets. You need to add more horns to it, and then it'll collapse properly. And that's not really the case either, right? We just get more impulse elements out there because there are more high frequency point sources in the array. Okay, now let's compare this to like number of cabinets in adaptive, right? Here's 6 cabinets of adaptive, like the first one you saw in the first example there, and voila, this is acting completely like a single acoustic source, all the way out to about 12,000 hertz here, 12,000, 13,000 hertz. No additional impulses in it. You can see this is acting like one speaker. If we match the cabinet counts for the deeper array, well, same thing applies. We could just get more impulses in the mechanical, but yet we still say a single impulse, single acoustic source in ANYA or in adaptive. And that's kind of the secret sauce, right? It starts out as a single acoustic source, as a single cabinet, and remains a single acoustic source no matter how many cabinets you add to the array. The math stays in place, and then we can manipulate the vertical. So if we start looking at angular aspects of both arrays, it really is just a story of angular resolution here, right? Whereas in a mechanically articulated line source, if we want to increase vertical coverage, we typically have to increase the cabinet count. This is especially true when it's steep, when we have a steep coverage. I mean, I'm sure you guys have run into the counterintuitive thing that happens when you're in a short, steep place. It may not be a very big capacity, but yet it requires a very long line of mechanically articulated in order to cover it vertically. That is not the case with adaptive. The adaptive products, their ability to cover a vertical geometry is not dependent upon the length of the line. So here, as I mentioned, in mechanically articulated, we would have to add more cabinets in order to cover a geometry. In Adaptive, we can go 90 up and 90 down and anything in between, and be able to cover this geometry vertically, and not only cover it vertically, but be able to cover it asymmetrically as well. Jonas is going to give you some examples of that when he does his section of it. Okay, so just to drive the point home here, as we need in mechanically articulated, we need more cabinets to increase vertical coverage. And if we don't use them, if we create extreme angles on them, then we're really breaking apart the line math that existed, that was there in the first place, and makes it tougher to keep really solid frequency response in play. Whereas even with 4 cabinets of adaptive, we could do plus 90 or minus 90 and anything in between, right? I mean, if you were, I do this kind of out of comedy. If you wanted to do this with mechanically articulated, right, you would just have to keep adding cabinets until you get to the 180 mark, right? Whereas in adaptive, we can do anything asymmetrically in that same range. Okay. So I added this last slide because the times I've given this kind of presentation to other people, they've the light bulb has kind of gone off in their head, and they've thought, hey, well, if you're not using a horn per se on your high frequency drivers, is it as efficient as a mechanically articulated box that is using horns? And I mean, it's a great way to look at it, a great question. And I always love the answer I'm able to give here. And that is that, look, this is a horn. Okay. The cabinet in and of itself is a 70-degree horn for Anya. I think it's 90 degrees for Anna, well over 100 degrees for AC6. So the cabinet in and of itself is the horn. And as we add them together, as we stack them together, guess what? We're creating one big horn. Right? We're not creating a stack of horns. We're actually expanding the mouth of that horn and the capabilities of that horn. If you were to look at it this way, it would really be, you're creating a 70 by 180 degree horn capability here. And this plays really well for the guys that say, well, we want it to be a point source. Excuse me. And you really should be able to do all of this with one cabinet. Well, there you are, fellas. I mean, it is one cabinet. That is mathematically and acoustically one speaker cabinet hanging in front of you there. So, it'll offer the best acoustic phase of really anything that's out there in this style of speaker system. Okay. So in terms of efficiency, it is actually wildly more efficient. The same input signal to this versus the same input signal to the same number of cabinets would be no contest, right? So let's just kind of wrap up my section of it here. This is, I kind of termed this, why does adaptive actually sound good? And this is a list of the reasons, in my opinion, primarily because it is the only large format PA system out there that is able to establish and maintain a single acoustic source throughout its entire process. It starts as a single acoustic source and it ends as a single acoustic source. The ability to kind of polar form, which is kind of how I've labeled this vertical capability, it really is polar forming, and it results in really good, consistent audio coverage over even a complex geometry, where we can be nimble, we can be asymmetric with it, and be very predictable with it. And this is an important one. I think this one gets glossed over a lot, just simply because there are so many systems out there that are mechanically articulated. But adaptive actually gives you the ability to have what I've kind of termed it impulsive high frequency, right? Impulsive high frequency, as opposed to diffusive high frequency, meaning coming from many different areas in the array and causing all kinds of issues. So, impulsive high frequency results in what? It's going to sound great on percussion. Anything that's got high frequency transient in it, cymbals, S's, all of those things are going to be really, really superior if you can have that coming from a single acoustic source all the way out to those high frequencies. That's where the rubber meets the road, from my mind, in terms of detail, right? Especially on intelligibility, and especially on intelligibility at distance. It has a huge impact on that. And finally, this is kind of an unsung hero of adaptive in my opinion, and I experienced this the times I had it out with Petty a few years ago. We really made note of this. It seemed like daily, where we were talking about, wow, the room tone sounds different with this PA. And that has to do with it being a full frequency single acoustic source, right? You're now exciting the reverberation with a point source, not, partially point source, partially diffuse. So, it's like taking one signal and sending it into a reverb. It's gonna sound good. And the room tone is actually going to sound better. All right. All right, so that's my half of the presentation today. I'm going to turn it over to my friend Jonas here, and he is going to take you into the real world and show you how this actually really works in the real world. I'm excited to see some of these. I've seen some of these case studies he's done in the past, and the interesting thing is the installers of the world really get this. Like they understand what's going on here, and this has been a very attractive thing for them. We just got to get the guys in Concert Sound to understand it and hopefully whet their appetite a little bit for it too. So I'm going to stop sharing here. Jonas, you can take over.
All right. Thanks, Robert.
Thank you,
Yeah, that
buddy.
was
Talk to you soon.
fantastic. I don't think anyone has ever really kind of uh, distilled that information about how that works with adaptive compared to other traditional line sources before. I think this is really a great explanation of, some of the benefits of this. So what I want to do today is I want to address a little bit of what adaptive as a whole is. So Robert's kind of given you a really unique look on how it's different than traditional line arrays. But what I want to do is get into like what is adaptive. We keep calling this adaptive. Robert mentioned Anya, some other things. So what I want to do first is talk about that adaptive is more than a product. It's a complete platform of audio control technology, right? So it's a whole big uh, system of multiple parts. Okay, so there's different tools and pieces and building blocks that all go together that work together that we call adaptive. Okay, and it's both software and hardware. So I'm going to get that into a minute as well. Um, but so let's take a look. So in adaptive, we have multiple things like several products that we make that are all what we call adaptive. We've got different model names: Anya, Anna, AC6, Auto, and such. And then so it's not just a loudspeaker, and some of these things can work together. Some of them could be, multiple building blocks in one system. But uh, um, for the most part, it's also working together as a the software is not just a prediction software; it is the control software. Okay, so that's what I kind of want to get that into. So to reiterate kind of what Robert was showing you earlier, I got a little deeper look into an adaptive mid-high engine for this. This one is Anya, and you could see here in the center. That's the backside of all of the 1-inch compression drivers, which physically are actually larger than 1 inch. So how do we get them to be 1 inch spacing to make that technology work? So if you look closely at this image, you could see that they're actually physically staggered next to each other, and their exits are 1 inch spaced diffraction slots. So if you kind of put that together, that's kind of explains how we got a bunch of 1 inch compression drivers all to work like that. Then flanking the mid-high section there. Okay. So, and whether it's Anya, Anna, or even AC6, all of the fundamental principles of driver spacing and wavelengths are the same. Okay. So if you take a look at this is an AC6 acoustic module, you'll see the same thing, even though these aren't compression drivers. These, in this case, they're 1-inch dome tweeters, but they are they adhere to the exact same physical spacing principles as everything adaptive. Okay. All right. So how does all this work, really? Right. So Robert kind of talked about how we can create asymmetrical things, change the shape from narrow to wide, all of those things. Okay. So that's kind of what I want to get into, a little bit of how this actually all works. Okay. So there's really 3 steps into this. The first step is that we or you, the user, all right, you create an audience target. So that might be, a flat floor. That could be a balcony in a an orchestra level. That could be an arena seating layout. All of those things. So you create these audience targets, right? And so I'm calling them a target because the way adaptive works, it's going to look at those targets, and the software called resolution creates the directivity, the required SPL, and the frequency response for those targets by using the known physical resources of whatever we decide that we want to use. Okay. So it's kind of generic between all of the adaptive products in the way that these work together and create directivity based on the target. So the first step is you creating, where the audience is. The second part is the software is creating all of the directivity, frequency response, and SPL for those audience targets. The last step is we send those parameters to the physical devices. Okay. So that's the 3 steps. It sounds pretty easy. It can be. We have a lot of tools to make it super easy and user friendly, as well as have the ability to, be very, what I say, surgical with it as well. So let me just show you a little bit how this works. So this is kind of a visual representation of kind of what I just showed you. This represents some of the software. You could see there's an array in the image, and there's some audience areas defined here. So that array doesn't have to be Anya. It could be an Anna, it could be AC6, it could be 5 cabinets, 20 cabinets. It doesn't matter. What happens is the software then takes that array and what resources it has and creates the directivity to match or adapt to the targets that we defined in here, which are in this case of the audience areas. Okay, so it kind of backwards calculates what kind of SPL and directivity is needed to get to this furthest point, all the way up to this point up here in the front. Okay, and so the result of this calculation might look like that in this case. Okay, so that's our directivity pattern, and this is created in the software automatically based on the relationship between the array resources and the audience targets. Okay. Then on top of that, not only are we creating in software the directivity shape and creating an even SPL polar shape to match the target. We also analyze the overall target frequency response, and they're with a built-in target curve that we're trying to achieve. We can then use EQ normalization across all of our audience areas and use some pre-emphasis filters to create, EQ normalization over that entire audience area. And then also, as we get further and further in distance, we can also add some air loss pre-emphasis filters to correct for a balanced frequency response as you get farther away from the array. So all of this is happening in resolution. This is part of the adaptive algorithm. So when you define the audience area and add an adaptive array of resources into the software, it's going to take all of these things into account and create the polar SPL and frequency response using all of these tools in the behind the scenes. Also, another thing, when we create multiple arrays, there is an amount of array optimization going on as well to also enhance the point source optimization between multiple columns. Okay, so all of this is happening in resolution. All right. So the next thing I'd like to show you is resolution. So on our website, if you're not familiar with already, you can download this. It's free. It is a 3D mapping software for all of our products, but it's also the control system for adaptive. Okay, so let me switch over to resolution. And there we go. So what we're looking at now is this is resolution. This is a 3D view of some free space, and we see an audience area here. So I'm going to show you kind of the steps of how adaptive works, and this will help wrap your head around how to use adaptive products and why there's so many benefits. Okay, so I can take this audience target. Let's just make it bigger. I'll make it about 100 feet long, kind of put it in the middle. It's about 10 feet from zero. And then I'm going to add an adaptive array. In this case, I'm going to use AC6, but it could be any of the adaptive arrays. It's going to do the same thing. I'm going to put it off the ground a little bit. And you might notice, if you could see my screen here, that it's doing something. There's a little thermometer bar at the bottom saying finish acoustic model build. So all I did was define an audience area and add an adaptive array, and it automatically created some sort of coverage pattern for this space. So if I look at a side view, you could see there's some sort of directivity shape that's gone on here to cover this area. So what has happened, and let me explain this, is this adaptive array has, let's say, it looks forward and it knows what it can see. So it can see this audience target in front of it, and it knows that since we've defined it as an audience, that we want sound to be there, and it knows where it starts and stops. So it's going to create the directivity to match this. Okay. And it's also going to create even SPL, frequency response, all of that over this one area. So if I put in a couple of microphones here, we could see what the levels are. So and how close they are to each other. We can then look at a frequency response graph and see how close they are to each other. Okay, so we could see all of that, and that's all happened automatically just by defining this. Okay, so let's take a look at the side view again here, and now I'm going to move the array up. So let's say we'll mount it really high this time, and I'll stay in this side view so you can see this. It's going to do the same thing again. Okay, but now it's in a new spatial relationship with this audience area. And so it's going to create a different directivity pattern or polar pattern to match this seating area. So you can see that there. It's a little less directional because it's up high. It has to open up the directivity to cover front to back. And there's a whole bunch of tools that we can do to adjust for that. Okay. So you'll notice that I'm not creating a beam and aiming it. I'm placing an array and I'm defining where the audience is. Okay. So I could put this here, define the audience, and it's going to create the directivity, SPL, frequency response, all of those things based on this relationship for me. And I can adjust it if I want to. Okay. So let's take a look at this pattern here that we're about to see. And let me show you what happens. If we add an additional surface, because Robert mentioned to you that we could create asymmetrical stuff. So let's do that. I'm going to create something a little ridiculous here, or we'll make a little balcony thing. We'll make it really big, really high, and just we'll take the array. We'll kind of put it somewhere here in the middle, see what happens. So right now, what the algorithm is doing is it's looking ahead saying, I see these two surfaces, I need to put sound there, they're audiences, and so it's going to create the directivity based on whatever resources it has in the adaptive array and create coverage there. So you can see here I've created a very complex asymmetrical coverage pattern to cover both a balcony and an orchestra level. Okay, and then another thing I want to show you is Robert mentioned that, we have the capability of 180 degrees, in any shape in between, right? So let's do that as well. So I'll take my balcony now, and I'll just go here, put it way up here. So I've got a surface here, and I've told this is still an audience, okay? And let's see what happens. So it sees it, and it's going to try to put sound there as well as on the floor. So that would be pretty hard to do with any other type of traditional array, but with adaptive it's very easy actually. So let's take a look, and you can see that's a pretty amazing shape that we've come up with. Okay, so that's kind of in a nutshell how adaptive works. And then once you have decided that yes, this is the desired directivity pattern that we have. So far I'm working with virtual things, right? So this is all offline. But once we have decided that this is exactly what I'm looking for, I like what it's doing, okay, that looks great, I can then go to our network, find devices online, and then my last step would be to push this math into the devices, and now it lives in those devices, whatever I have out there. Okay, so again, this would be the same if it was, I'll just show you real quick. If it was on your Anna, so let's put some Anna in there. Let's put some Anna. Let's put a few boxes in there. Okay, let's just put a stack in there. It's going to do the exact same thing. Okay, so what you just saw happen with the previous array, so whether it's a stack of Anna or it's a stack of that array, the process is the same. It's going to behave the same. It's going to create directivity based on whatever resources it has. You can see that there. Okay, so as I was showing you earlier, with adaptive, we can very easily create surgically precise coverage based on whatever audience area that we have. So all things being equal, some of you, if you've seen me present before, I've seen this kind of image. On the left, you'll see a traditionally articulated array, processed and shaded as best we can to cover both the balcony and the floor, and it's doing a pretty good job. But with the equal number of adaptive boxes, you'll notice that we have much more surgical, precise coverage that we're able to achieve. Okay, so think of it as a higher resolution array coverage that you can get out of it as well. So in that polar pattern, right? Another thing that's not always obvious is, Robert kind of alluded to this, is the array size. Okay, on the left over here, we need all these boxes to cover from the front and the floor and these upper boxes up here. On the right, we may not need that many boxes to get the same result, both in SPL and even better coverage. So oftentimes you can use shorter arrays to get similar performance out of what you would traditionally need more boxes for. Okay, so it's very difficult to compare box for box between adaptive and any other traditional array. I mean, Robert kind of alluded to some of the reasons why this is, and this just shows you, especially in this slide, how that is very different. So with half the number of cabinets, I can get a similar, if not better, performance with fewer cabinets, less weight, and all that in the same space. Okay, so let me show you some real world examples of that. Some of these photos are some installs that have used shorter arrays. So you see the one on the left, we've got a bunch of really large video screens. Well, it's real hard to get that real estate to hang big, large traditional arrays that are needed to cover, some of that complex seating. And so with these shorter arrays, we're able to do that and still get the performance that is needed, for these performance systems. Okay, the one on the right, you see it's very, very low ceiling, and they still have video screens, and we're able to get line array performance out of something that's very, very short. Here's another one. I think one of you guys, I think Andy's online watching this now, but this is, I love this example because you almost can't see where the loudspeakers are. But if you look up in the lighting grid, there's a left, center, right array up in this grid covering this entire room, every seat, and adjusted to get very, very even frequency response in this room, much more than we could have gotten with a traditional array. Okay. And I love showing this example, complicated coverage. This is just a room that's very difficult to do with any array that exists. And, this was a stop on the Hamilton tour. I think I can mention that. And we were able to, what I was told was in this space was the first time ever on of them, these Broadway guys in that room getting a what they would call normal sound in every seat in here, just as they would have gotten in a theater that wasn't so complicated. So that was the first time because they had the use of adaptive. Okay. Then also multi-channel systems. Now this could be stereo, could be LCR, could be immersive, whatever you want to call it. Whatever multi-channel system you're working with. A lot of times with traditional arrays, I love this example. This shows a matrix point source array system. So with adaptive, it has a unique ability to basically cover a very, wide space with the same SPL response and, level from one point. So you could see in this image here, kind of, it's a very wide room, and we've got an array that's almost 180 degrees wide. And it's basically, in this case, this is Anna. So it's broken up into two pie slices, if you will. So one pie slice is creating specific vertical coverage based on its distance and throw front to back. And then the other pie slice is also doing the same. And then they're optimized together. If you wanted to have more pie slices, you could use Anya, which is even a narrower pie slice. For instead of two, you would have three, and you can create even more high resolution coverage in here. But it's a very unique thing that it's very difficult to do before adaptive. And then another unique solution with adaptive is changing coverage based on use. So let's say you're not going to use the whole arena today. We're just going to use the lower part of the system. In any other system, you're probably going to have to turn boxes off. Okay. And what is that? We all know what that does. That changes your directivity of whatever arrays you have, and might not give you the exact same sound and queue of the arrays. Well, with adaptive, we can use the entire array, whether we're covering the part of the arena or the full arena. We're not turning any boxes off. We're just simply changing coverage of the entire array. Okay. And then another unique application is in noise mitigation. So this is a great example. I like to point out, you can uniquely take adaptive and focus it specifically where it needs to be and have huge relative reduction of SPL outside of that range. So again, something very, very unique to adaptive that can solve a lot of these issues. Okay. So now you've seen some of those benefits. You've seen how it works. Let's talk about some cost examples. Okay. We've heard from, a lot of people think it's very expensive because in adaptive, a lot of the adaptive products, they're all self-powered with multi-channel amplifiers and DSP all built in. So one cabinet, when you take a look to a passive box, might be more expensive. But let's look at a comparable system that we most of us should understand, like say a church with LCR, a theater with a left and right system, or an arena. And let's actually do some real world comparisons. Okay. So let's start with that church. So this is an interesting example. So we've got the church. It's a similar one that we saw earlier. So we've got a LCR system that we're covering the seat with, and then we're trying to do the same thing with a traditional array. This is a variation of 110 and 80-degree cabinets here to try to cover this area as best we can with an LCR system. Here's some examples of coverage. So what you're looking at here is the bottom left image is the house left array, and let's see. And then the top right image is the center array. Okay. And you could see the variation in coverage there. Let's take a look at the same thing with the adaptive. Okay. All right. So if we take a look at this, this is the bottom left is the center channel. No, sorry, house left channel of the adaptive array. And the top right is the center channel of the adaptive array. So you can see that with it's essentially a shorter array, but we're actually able to get more consistent coverage. And you're seeing the distribution chart here of SPL. So we could take a look here. I'll go back and forth so you can see that there over the entire area. Okay. All right. So now let's take a look at cost. Okay. So we're thinking that this is a real world example. We've asked a AV integrator to do some of this work for us to figure out, what kind of cost differences this might be. Okay. And we can see that when all things included here, the adaptive system in this particular case comes out significantly less when we look at all of the elements that go into the install. Okay. And here again is that image of that venue. Okay. Let's take a look at another example. This would be a theater left and right system. So in this case, I'm going to compare a two tall AC6 array. So that's a 6-foot tall array mounted to the proscenium left and right versus a compact double 6-inch line array that's flown left and right. Okay. And we could see the coverage difference in the preciseness of it as well. And let's take a look at the cost of installation. So both arrays are self-powered. So really the cost of installations are probably going to be mostly the rigging and such. So we took a look at that, and it's pretty close, but still the adaptive is a little bit less in the end when we're looking at comparatively, even though the actual speakers might cost a little more. In the end, the install still kind of was a wash between the two. So you can take a look at that. And then here's an image of something very similar to that. So in this case, this is an AC6 array left and right. You can see it kind of blends into the proscenium opening here much more than a flown bent traditional array would have been as well. So last one on cost. I like to show this one. This is a real life example. This is a sports arena. So in the sports arena, we have a distributed system because it's hockey. So they've got the hockey glass wall around, around the court. And so we need to cover straight down as well as all the way up into the main seating. Okay. And in this case, what you're looking at here is a system design that uses a mix of distributed arrays of ANA. They've got some auto subwoofers in there, and you can see that it's distributed all around the court. so we can cover straight down in front of the glass. The alternative for traditional array is a lot more cabinets hung at extreme angles, trying to do the same thing. Okay. And we'll take a look at the cost comparison of this install. This is actually a real life situation. So we know that these numbers are real. And you could see that in this case, the adaptive system also won in price, not only just on its ability to perform, better in the space. Okay. And I have a final image. I'll let you take a look at that for a second. And here's the image of that sports arena installed. Okay. All right. So I hope that was informative for you guys. That concludes what I have for you. I'm going to stop sharing my screen here and bring Robert back. So I hope you guys like that. And I hope that, this was helpful to you guys.
That's great, Jonas. I get something out of that presentation every time you give it. It's really good, man. One of the things I always pull from that when you give that presentation, Jonas, is and I think it's a hard thing to get across to the market sometimes, is that you cannot just compare adaptive cabinet to cabinet
Mm-mm.
with a conventional array.
No.
If for no other reason, just the sheer amount of componentry and amplification within adaptive compared to that other cabinet, so it requires a little bigger tunnel down to really understand what's going on and compare apples to
Right.
apples there, right? That's great.
Right.
All right. Well, folks, that is our first webinar in the can. Thank you for attending. We really appreciate you guys coming in for this. We are going to certainly have more of these. As I mentioned at the top, this is the beginning of a series for us. We plan on having a lot more webinars on resolution training, on case studies, more deep dives on adaptive, et cetera, over time. So please stay in touch with us. I'm sure some of the replay will be available soon on the website and probably on YouTube, something along those lines. So stay in touch with us to gather more information on this. Obviously, EAW is kind of trying to march back into the fore in the industry. There's some really great things going on here. I am really excited to be a part of this all. So thank you again for coming, and we will hope to see you on another EAW webinar. Thank you, guys. We'll see you next time. Thanks.
Thanks.
Bye-bye.